Okay, welcome to Robotics 2. As I said in today's class, we are going to start this very important chapter, which is lesson number 6, Dynamic Model and Parameter Measurement. The chapter, the textbook does not do justice to this topic because where the equations are derived cursorily without going into the depth of how those equations come about or what are the practical applications of those equations. So what I'm going to do is, first in today's class, I'm going to give you a brief overview of the material as discussed in the textbook, wherein you would see the equations derived in Newtonian equations like secondary. It's like just a vector, but each equation is expanded in 3 dimensions because we have a rigid body which has x, y, z, roll, pitch, yaw. So basically there are 6 degrees of freedom. So then what I'm going to do is I have a supplemental lesson which actually talks about the individual derivations of those equations. I would discuss that. But let me tell you, don't get scared. These equations, when I first saw as an undergrad, I got scared. Wow, these equations are super complex. They are really not. The basic concept is force is equal to mass times acceleration, torque is equal to I times angular acceleration. All these equations come from those fundamental concepts. And I will try to explain to you. And please understand, once you understand the basic dynamic equation, whether it's a quadcopter, whether it's an octocopter, whether it's a fixed wing, whether it's a glider, or whether it's a kite, the equations are the same. Let me repeat. I'm gonna give you the most generic equations that will be applicable for any flying vehicle. What would change on each vehicle is the control surface. What that means is, in the case of airplane, you have wings. In the case of quadcopter, you have rotors that give you thrust. In the case of glider, what you have is gliding surface that is giving you the lift. In the case of a blimp, what you have is you have that big balloon that is actually making the whole thing float. In the case of tilt rotor, it takes off as a helicopter and then transitions to the airplane. The equations, the dynamic equations, the basic dynamic equations are going to remain the same. What would change is inertia properties, control surfaces, and basically control authority, what we call it, is going to be different. So please understand, this topic is super duper important. I would actually go through the basic quadcopter analysis that is discussed in the textbook. That should give you some sort of understanding with the aerial robotics class that you are doing. But the basic equations are the same for all aerial vehicles. For all UAVs, the basic equations are same and they come from Newton's laws. Okay. So what are we going to do in this chapter? In this chapter, so whenever you have an aerial vehicle, you are going to have forces, you are going to have moments, you are going to have masses, you are going to have mass moment of inertia. So typically, you are going to have some sort of dynamical model. Since that helicopter or aircraft is flying in air, you are going to have some sort of aerodynamic forces like the resistance because of the air or the lift or drag because of the air. Then you are going to have some sort of input. So for an example, in the case of aircraft, you are going to have thrust, which is given by either the props or the jet engine, but which is actually perpendicular to its x-axis. In the case of quadcopter, again, you are going to have thrust, but in that case, the thrust is going to be parallel to the z-axis. Then we will have some type of aerodynamic drag model, depending upon the shape of the aircraft, whether it's quadcopter, hexacopter, octocopter, or maybe a kite. You are going to have different types of aerodynamic forces. Then we have to understand what are the different model parameters, whether it's an aircraft or whether it's a quadcopter, the mass and inertia properties for those aerial vehicles are going to be different. So we need to take into account those. And at the end, we would have this conclusion. Let me tell you one thing. I'm not gonna ask you to derive these equations, because what we would do is we would use these equations to construct a simulation and the model for the aerial vehicle. And the good news is MATLAB has actually coded all these aerodynamic equations, wind models, then the turbulence models, everything is inside the MATLAB aerospace block set and UAV toolbox. What we will do is we will use those functions, we will use appropriate transformations and construct a complete simulator for that matter. You can construct a simulator for quadcopter, you can construct a simulator for a fixed wing, or you can construct a simulator for a tilt rotor. So we are gonna do that. So believe you me, for next 2-3 weeks, we would be spending a lot of time on these aircraft equations, quadcopter simulations, and how to change the control and all that stuff before we move on to the perception part. So what is the basic idea? And the basic idea is we are looking at an aerial vehicle that's rigid. And that is the first and foremost assumption, that the aerial vehicle that we are studying is rigid. The dynamic model is rigid. And then what we do is, depending upon the type of control we use. For example, in the case of aircraft, what you have is you have ailerons, you have rudder. Basically, the ailerons will allow you to lift and drag. Basically, they will change the pitch angle. You have the rudder that will change the yaw angle. In some aircrafts, you don't have ailerons and elevators separately. You have them together. So basically, an X-wing type of or flying wing type of aircraft, basically you combine multiple control surfaces together. And then at the end, you have some sort of propulsor model. So you can have a turbine, or you can have a prop, or you can have a pusher configuration, or you can have a puller configuration. Pusher means basically you have the prop at the back of the aircraft. So basically aircraft is pushed, or in the case of puller, you have the prop in the front of the aircraft. So aircraft is pulled. In the case of quadcopters, you can have the motors mounted on the top, motors mounted on the bottom. So the configuration may change, but schematically, you're going to have a rigid body model. You're going to have equation of motion. You're going to have some sort of control algorithm, control surfaces. And finally, you're going to have some sort of propulsor that would actually propel the aircraft forward. What are the main important assumptions when we design a dynamical model? Either it's an helicopter, multicopter, or fixed wing. We start with, it's a rigid body, moment of inertia are constant. This assumption is okay for small UAVs, but please understand, if you have a UAV that is using gasoline, as the UAV is flying, the amount of fuel decreases. In other words, the mass properties decrease. In other words, the moment of inertia, they change. So basically, when we assume the second assumption that the mass and moment of inertia are staying constant, we are looking at small aircrafts, battery operated aircrafts. Then geometric center and center of gravity of the multicopter is the same. What that means is mass is located where the center of gravity is. And this assumption is true and valid for small UAVs, but this assumption may not be true for load carriage. So for example, once you have a UAV that is used like Amazon drone that is grabbing the package and dropping the package. As soon as a package is grabbed, its mass and inertia and other properties will get changed. If the gripper is off center, then basically your center of gravity is no longer coinciding with the geometric center. The next assumption is the multicopter is only a question.
Yeah, quadcopters, they are designed to be unstable, right? How will assumption 3 or 2 of that?
Quadcopters are
Designed to be unstable, right? Like for maneuverability and those all.
right. So, but the issue is what it means. If you want to, you have a quadcopter, it's designed to be unstable. But if I want to balance it at the tip, you agree with me, I'm able to balance the quadcopter at the tip. You agree? What that means is its geometric center and the center of gravity is coincide. However, when the quadcopter is flying, clearly, depending upon the configuration, the geometric center and the center of gravity may be offset. But in that case, the controller algorithm would come in the picture and try to align. Any other questions? Ask. If you have any questions, please ask. Now, in quadcopters, we assume that the only force that the quadcopter is withstanding is the gravitational force, and gravitational force. Please understand. In the last class, we talked about the inertial frame, which is the Earth-centered, Earth-fixed frame, and there is aircraft body coordinate frame. Aircraft body coordinate frame is attached to the aircraft and that is rotating. The gravity vector will always be pointed towards the down direction in the Earth center, Earth fixed coordinate frame. So that is something that you have to take into account. In other words, the body frame of the aircraft may or may not be aligned with Earth center, Earth fixed, but if you want to resolve the gravity, you would have to use those transformations that we talked about to find the component of gravity on the aircraft. I give you a very simple example. If your aircraft is in level flight, if the aircraft is in level flight, you agree with me, the gravity is acting down. But if aircraft is pitching up, even though the aircraft is pitching up, the gravity vector or the weight is going down. This is going to give you two components. One is going down and one is towards the x-axis of the aircraft. So what happens is the gravity vector is always aligned with the down in northeast down, Earth center, Earth fixed coordinate frame. And here is the last assumption. So basically this is just for convenience. If you have odd props, so prop number 1, prop number 3 will rotate counterclockwise. Prop number 2 and prop number 4 would rotate clockwise. So yeah.
Assumption for first point is that gravity it's only under gravity and problem.
Yeah.
What does that mean? Are we ignoring something?
Yeah. So basically, yes. So what happens is when the aircraft is flying, it's creating unsteady aerodynamical effect because of the turbulence. And these unsteady aerodynamic effect give rise to additional forces, these are localized forces in that region. But we ignore those forces for the analysis. And actually that is there is a lot of research going on in ultra high endurance UAVs, where what they do is the ultra high endurance UAVs modify the control surfaces based on the localized airfield. In other words, they can ride just like birds, they can ride on the air currents and basically conserve the power. But what we are saying is we are ignoring those teeny tiny disturbances. We are just looking at two types of forces. One is the thrust of the propulsor, and the second one is gravity. These are the two forces that we are going to study. But this assumption is good for UAVs that are flying at slow speeds. If you have UAVs that are flying at very high speeds, then this assumption is no longer valid, because in addition to the aerodynamic effect, you get non-linear aeroelastic effects that come in the picture that affect the performance of the aircraft. But as far as we are concerned, yeah, any other question?
Yeah. First, so you said that the small unstable, like unstabilizing forces are ignored.
Yeah.
But then how are we developing the control model without balancing, so to say, balancing the quadcopter?
Yeah, so basically, when the quadcopters are flying slowly, then those forces are not significant. That's what it means.
Okay.
And I'll give you a very simple example. If you have quadcopter that is flying steadily indoors, as soon as you take it outside and there is wind passing through, it will no longer be stable. That is because that control system is not designed to overcome the disturbances because of the wind load or unsteady aerodynamics. That's what. Okay. Any other question? If there are questions from online students, please put it in the chat window. Okay. So this is how this chapter is laid out. So, and I'm going to give you very few basic concepts that you have to remember. Whenever you analyze any aerial vehicle, first step is to understand the kinematic model. What do I mean by kinematic model? Kinematic model deals with positions and velocities. Linear positions, angular positions, linear velocities, angular velocities. That is called as the kinematic model. That is the very first step. Kinematic model for all the airplanes is same. And that kinematic model is used to find out the orientation position of the airplane. So there is something called as inertial measurement unit, which is 3-axis accelerometer, 3-axis gyroscope, and you have 3-axis magnetometer. Sometimes you have GPS. So and you have the same thing in your phones. So I don't know if you look at your IMU calibrator or IMU, if you look at your iPhone app or Android app, you would see some sort of IMU app that will tell you orientation, position, potentially velocities of your phone. So that is the first model. So ignoring mass moment of inertia, we just focus on the kinematic model. Kinematics is motion. So you have a linear motion and you have angular motion. So those are the motion kinematics parameters. Second part is first you have to resolve the kinematics. Once you know the kinematics, you use that information to solve for dynamic equation. There are two dynamic equations. One is dynamic equation is for translational dynamics. F is equal to ma. That is Fx is equal to max. Fy is equal to may. Fz is equal to az. Mass in x, y, or z direction is going to remain the same. Now you have the dynamic equation in the rotation coordinates, which is something like P is equal to I alpha. That is the basic version of it. But please understand, I in each axis is different. So Ixx, Iyy, Izz is going to be different. So you are going to have those dynamic equations. And remember, force is equal to mass times acceleration. That force term would include thrust, aerodynamic lift, aerodynamic drag. So that goes in there. Look at the T is equal to I alpha equation, where T is torque. So the thrust multiplied by the lever arm gives you the torque. That goes in there. And clearly, those equations of motion may be unstable. To stabilize those, what you have is you add this control effectiveness model, which means how do you vary those forces and torques so that the dynamical system or the equation of motion is stable. And then you add the control effective model and you add the propulsor model. And then basically that gives you the whole multicopter, or for that matter, any aerial robot control model. If you look at the textbook, these are the equations that are given. Let me tell you, these equations, they look very simple and harmless, but they are not. They are very complex. So rigid body kinematics model deals with position, linear position, angular position, linear velocity, and angular velocity. In the last class, I briefly talked about three different ways of discussing rotation. One is Euler angle, second one is rotation matrix, and the third one is Cottonian. We will start with Euler angle model because that's very easy to understand, that is very easy to implement. I will give you some background information on rotation matrix and Cottonian, but for practical applications, people usually use Cottonian because of singularity issues. Euler angles have singularities. Now, let me give you a brief overview of what these equations mean. I want you to look at Euler angle model. On the left hand side, you have E, P dot is equal to E V. P dot is rate of change of position. E means Earth center, Earth fixed coordinate, and which is given as the velocity of the vehicle in Earth center, Earth fixed coordinate. This one line equation is actually three equations because there is velocity in x direction, velocity in y direction, and velocity in z direction. That is what that equation is about. Also, please understand, you cannot add dollars to pesos, dollars to dollars, pesos to pesos. In other words, if you have the velocities on the left hand side, they are expressed in Earth center, Earth fixed coordinate frame. You cannot equate that to aircraft body coordinate frame. Everyone understood? Dollars to dollars, pesos to pesos. You cannot equate velocities in the Earth center, Earth fixed to the velocities in aircraft body frame. You would need to use a transformation matrix that will make that whole thing consistent. Everyone understood this? So this simple innocent looking equation is actually three equations that consist of a transformation matrices, and I will give you those matrices. We'll derive those step by step. Second equation. This is also a very innocent looking equation. Theta dot is equal to W multiplied by B omega. This B omega is nothing but the angular rates of the aircraft. So W is the rotation transformation matrix that will take these body angular velocity and convert those to inertial angular velocity. And I cannot emphasize this enough. So please try to understand. And this is actually super important, this concept, because there is an entire field of inertial navigation and tracking that is based on this equation. So I want you to visualize that this is a UAV. Initially, the UAV is in simple hover. So in this particular case, you agree with me, my Earth center, Earth fixed coordinate frame and the UAV coordinate frame, they are aligned. In that particular case, only at that instant, this is very important, only at that instant, the roll rate, pitch rate, and yaw rate, they align with the inertial angles, inertial rates. Once again, I repeat, this is the UAV. Let's identify the coordinate system. So this is north, east, down, north, x, east, y, down, z. You agree with me? So north, east, down, north, east, down. This is the coordinate frame. This is my Earth center, Earth fixed coordinate frame that is fixed to Earth. initially my body center aircraft body reference frame is at the center of gravity of this aircraft. At this point, which is zero pitch, zero roll, the pitch rate, roll rate, and yaw rate is equal to the inertial rate. Do you agree with me? Are you with me so far? This is super important. As soon as this UAV rotates, its rate will no longer be equal to the roll rate, pitch rate, and yaw rate. Do you understand that? Because now this coordinate frame, so initially it was like this, it yawed. And when it yawed, its roll rate, pitch rate, and yaw rate is no longer, maybe yaw rate is same, but roll rate and pitch rate is no longer equal to the pitch rate and roll rate in Earth center, Earth fixed coordinate frame. Everyone understood this? Because this coordinate frame, initially which was aligned, is no longer aligned. Everyone understood this? This matrix W takes care of this transformation. So this matrix W takes care of that transformation. So now one thing, let's try to understand. I have this Earth center, Earth fixed frame. I have this aircraft body center frame. Initially they were aligned, that all we agree. After some time, the aircraft started going like this. And now you realize that my frames are no longer aligned. But when the frames are no longer aligned, the IMU, which is mounted inside, which is 3-axis accelerometer, 3-axis gyroscope, is also aligned like this because it's strapped down. It is glued to the frame, which means the rate and velocities and positions that are measured by the IMU are going to be inside the aircraft body reference frame that somehow I need to transfer back to the Earth center, Earth fixed frame, so I know how far this UAV has traveled or what is its current orientation. Everyone understood this? Now, I want to say something about this orientation problem because this orientation problem is not trivial. So, if I give you angular velocity, say my UAV is rotating at 10 degrees per second. My UAV is rotating in yaw 10 degrees per second. What would be its angular orientation after 1 second? Let me repeat. If my UAV is rotating in yaw in 10 degrees per second, my question is, if initially it started at 0 degrees, what would be its orientation after 1 second? You would say 10 degrees. That is perfectly fine as long as these two coordinate frames are aligned. Now imagine a case where the UAV is rotating 10 degrees in yaw and 10 degrees per second in pitch. Now if I ask you the question, tell me after 1 second what is the final orientation, you won't be able, you can't say with confidence it's 10 degrees in roll and 10 degrees in yaw. Why? Because in addition to those rates, the orientations have also changed. What it means is you will have to solve a differential equation to propagate those values. You can't just simply integrate. You're going to have the differentiation that actually comes in the rotation matrices come in the picture that will change those values. That is the inertial navigation problem, and we'll talk about it. More details on this will be coming for next 2 weeks. We are going to beat on those equations, come up with simulations, and show you. I'll show you how it works. Now, I want you to, for a minute, look at the rotation matrix model. Rotation matrix model, the first equation is same as Euler angle model because it's a position equation. But the second equation is different. Second equation, you have something called as R dot. which is the rate of change of rotation matrices, is equal to the rotation matrix multiplied by the frame, aircraft body frame angular velocity. And please understand, this is very important. If you want to solve this, you will have to use numerical integration. So this equation, if you want to propagate, so theta dot is equal to W multiplied by omega. If you want to propagate, you have to use numerical integration to propagate. And when you do that with numerical integration, there are issues with stability and all that. So we will deal with that later. Now, what happens with Cottonian? Cottonian is a four-dimensional hyperplane. So the first equation for the position or the velocity equation is going to remain the same, but the orientation equations Q naught and QV are different. Now, next part which I want to talk about is briefly is once you solve the kinematics equation, once you know the position, once you know the velocity, what next? Then you look at the masses and look at the inertia properties and incorporate something called as the rigid body dynamic model. Yeah.
Sorry.
Yeah.
Last slide.
Yeah.
So understanding the entire dynamic model, all we need is Euler's first equation, second equation, and since that is the same in rotation, this first equation is ignored. Second of the rotation, and then why do we need a Cottonian?
Okay. Cottonian. Why do we need a Cottonian? A short question with a very long answer.
Okay, we'll learn it later then.
So, and to be honest with you, if I try to explain it, I won't be able to do a good job. But here is my recommendation. Go to YouTube. There is a channel by 3 Blue 1 Brown, and he has 4 video lecture series on Cottonians, wherein what he has done, he has actually created very nice animation where he has given the geometric interpretation of Cottonian. So in a hyperplane. So that will make it very clear. But idea is Cottonian is like complex numbers, I, J, K, and you have a scalar. Basically, they overcome the singularity problem of Euler angle. So 90-degree pitch, you cannot resolve an Euler angle, but with Cottonian, you can do that. But and all the video games, all the signal processing, OpenCV, camera, all that stuff, they use Cottonian, camera calibration. The problem with Cottonian is Cottonian integration is unbounded. So what you have to do is every step you have to normalize the Cottonian. So what I would do is I have written the Simulink code with the Euler angle implementation. I have written the Simulink code for Cottonian implementation. I will share those Simulink files with you, and next time I will show you how that whole thing, how the whole simulation runs. Equations are similar, but Cottonian, when you propagate, you have to check, you have to normalize the Cottonian every iteration. Okay, any other questions? So this chapter is super duper important because there is an entire section on quadcopter simulation that is based on these equations. And we are going to start those quadcopter simulations in next class. So rigid body dynamics model. Newton's laws. Force is equal to mass times acceleration in 3 dimensions, x, y, z. And torque is equal to I times alpha in 3 dimensions, x, y, z. So you are going to get 6 equations in rigid body dynamic model. Depending upon the aircraft that you are using, the forces and torques would change. Which means if you have a fixed wing aircraft, you are going to have lift and drag of the aircraft wing, and you will have the drag of the aircraft body. If you have quadcopter, you will usually ignore the lift and drag because of the prop. You only include the drag because of the quadcopter body. Then what you do is you have forces and you have the external dynamics, you have the differential equation, and you want to make sure that the differential equation has negative real parts. Basically, the system is stable. So you have something called as control effectiveness model, and you have PID gains, or you add some sort of controller input that would stabilize that system. Now, next part, this equation may look scary, but don't be afraid. We are going to dissect this equation step by step. So please understand, this is the basic explanation for the rigid body model in Earth fixed coordinate frame. What this coordinate frame is, please understand, everyone understand the mass is going to be the same in x direction, y direction, z direction. That's why there is just one m. This EV dot is the velocity of the airframe in the Earth-centered, Earth-fixed coordinate frame. Earth-centered, Earth-fixed coordinate frame. Then you have something called as G. G vector will always be in the down direction in the Earth-centered, Earth-fixed frame. G vector is always going to be downwards in Earth-centered, Earth-fixed frame. And then you're going to have the force on the aircraft. It could be the thrust. It could be some sort of aerodynamic force, lift or drag. That force has to be in the aircraft body reference frame, because that is the force on the aircraft. So air cannot exert the force, air cannot give you lift in the downward or northeast down in Earth center, Earth fixed frame. So the forces on the aircraft will be in Earth center, Earth fixed frame. So what you will have to do is, you cannot add dollars to pesos. So at the end, all the forces, they have to be resolved in only one reference frame. Doesn't matter whether you resolve them in the aircraft body reference frame or whether you resolve them in Earth center, Earth fixed coordinate frame, they have to be in the same frame. That's why there you are going to have this transformation. That is the reason why you have this rotation matrix. And then what you do is, you basically differentiate the equation for the velocity. And once you differentiate the equation for velocity, again, it's a vector differentiation. So finally, you land up with this equation. And this equation, what you see here is this innocent looking equation. It is actually a super long equation with I think 6 components, and so it's actually 3 equations, like equation x, equation y, equation z, and we will look at that equation in the next presentation. But what I want you to understand is, at the end of the day, the first equation that I have shown you is nothing but the Newton's law, force is equal to mass times acceleration. And this comes in the picture because what you have is, you have the gyroscopic effect. You have the aircraft that is not going in only the straight direction, but the aircraft that is going straight and turning. That's why you are going to get the product of omega times v. Those types of terms will come in the picture. Yeah.
What is E3?
What is
E3?
E3 is actually the unit vector in the third frame, but I actually haven't told you what those frames are. So just you bear with me for a few minutes. What I'm going to do is, the next slide, the kinematics and dynamics equation, then I have actually shown each frame and wherein those unit vectors. But those are basically the unit vectors in that particular frame. Okay. The next thing is, we looked at force is equal to mass times acceleration, and the associated equation is attitude dynamic model, which is torque is equal to I times alpha. Now, please understand, P is equal to I alpha. That equation is only valid as long as you are applying that equation at a fixed point, applying that equation at the center of gravity, or applying at the equation where the relative velocities are zero. I do not know if you know this, but please understand. T is equal to I alpha, which is supposed to be the counterpart of F is equal to ma. That equation is valid only in limited cases. When T is equal to I alpha is valid. P is equal to I alpha is valid when the torque and or the moment are about a fixed point, or torque or moments are about the center of gravity, or torque or moment are at the point where the relative velocity is zero. Unfortunately, in the case of aircraft, you cannot have that assumption. That's why you would have gyroscopic torques, movements, and this cross product omega cross JB omega. That product will come in the picture. Now, this equation again is the equation in 3 dimensions, because you are going to have the rotation in x direction, rotation for torque in y direction, and torque in z direction. So this innocent looking equation, that simple equation, is actually equation with 3 terms. So this equation in x, equation in y, equation in z. And in addition to that, please understand, this is a vector. This vector is cross product with J. With J is a matrix. So finally, this equation is going to become a super complex equation. But don't be scared. This equation may look complex, but its individual components are very easy to deal with. Next part is we take this kinematics model, we take this dynamics model and use this for simulation. And most likely, when we simulate the kinematics and dynamics model together, the aircraft or UAV is going to be unstable. So what we do is we actually add control effectiveness model. So basically, we add some sort of controller to it. Now, this is the same these same equations that we talked about. One in Euler angle formulation, the other one is in the rotation matrix formulation, and the last one is in the Coulombic formulation. As far as we are concerned, we are going to stick to this model 1. So these are, and I cannot emphasize this enough, these are the equations for 3-dimensional quadcopter simulation. If you have done your aerial robotics class on Coursera, where Professor Kumar derived those equations, those are basically these equations. And what we are going to do is we are going to use those exact same equations to simulate the quadcopter. If you look at the MathWorks or MATLAB ASB quadcopter project, they are using this model 1 equation to simulate the quadcopter. Now, next part is how do you control? This is where it changes from aircraft to aircraft. For example, quadcopter in plus configuration, quadcopter in X configuration, the controller model would be different. If you have a helicopter or if you have a quadcopter, the controller model is different. So control effectiveness model is different depending upon the airframe that you are using, depending upon the configuration that you are using. So since we are talking about quadcopters, here is the basic thing that we should know. Quadcopter, basically there are 4 props. We are going to study 2 configurations. One is the plus configuration and other one is the X configuration. So what I want you to do is, I want you to look at the coordinate frame for the plus configuration. You have north, you have east. For X configuration, you have north, you have east. And the torque, basically that you have counterclockwise torque and clockwise torque. So 2 props, they rotate in clockwise direction. 2 props, they rotate in counterclockwise direction. And as per our convention, we said prop 1 and 2, they rotate in counterclockwise direction. Prop 2 and 4, they rotate in clockwise direction. So if you look at the thrust that is generated by a prop, that is given as CT, which is coefficient of thrust multiplied by the angular speed square. So Ti, which is the thrust generated by each prop, is given as CT multiplied by the omega speed square, where CT is a constant term, and that depends upon the geometry, that depends upon that you can use some experimental data or some CFD analysis and find out value of CT. The reaction torque, see, since the torque is going, the prop is going to rotate, prop has a non-zero inertia. So since it's going to rotate, it has non-zero inertia, it's going to generate some sort of torque. And that torque, the reaction torque, is given as MI is equal to Cm times omega square, where Cm is proportional to the diameter of the prop to the power 4. So these two are the very, very basic equations for quadcopter control authority. How would you control the quadcopter? You would control the quadcopter by controlling the speeds of props. Everyone understood this? Now, what I want you to do is, I'm going to ask you this question. And I don't want you to look at these equations, okay? I want you, let me ask you this question. I have a quadcopter in the plus configuration. I have this quadcopter in the plus configuration, prop 1, prop 2, prop 3, and prop 4. If I want that quadcopter to go up, what should I do? I should increase the thrust so that it's more than the self weight of the quadcopter. The quadcopter is going to go up. Do you agree with me? How would I increase the thrust? By changing the speed. I cannot just change the speed of one prop. I need to change the speeds of two props together. The clockwise props should speed up. Counterclockwise props should also speed up by the same amount, which means it will have the total thrust. Do you agree with me? That is exactly how you would do a thrust control or hover control of the quadcopter. Now, let me ask you another question. For a minute, don't look at the X configuration, look at the plus configuration. Remember, north is down. So north is down going in, north, east, down going in. So rotation about north, rotation about X is roll. So can you see that I want this plus configuration to rotate in the roll? What should I do? If I want it to rotate, what should I do? So what I need to do is, I need to increase the speed of one prop and decrease the speed of other prop. Do you agree with me? So that's what I want to do. So as you can see here, if I want to create the torque about x-axis, if I want to rotate in roll, W2 should go down and W4 should go up. You agree with me? Minus means going down, W4 means going up. So that is how you do a roll control. What would you do if you want to do a pitch control? Same thing. You would increase the speed of prop 1 and decrease the speed of prop 3. So you do the pitch control. And please understand, I'm talking about positive roll and positive pitch. What do you mean by positive roll? The quad is rotating in this direction, or quad is rotating in this direction. Now, if I want to control in z direction, what I have to do is, I will have to do the differential. I will have to say omega 1 and omega 3, you increase, omega 2 and omega 4, you decrease. That way, I will have a positive yaw rotation. Everyone understood this? This is the basic quadcopter concept. And now what I want to do is, I have these equations, tau x, tau y, tau z, and I have the equation for F, which is the thrust. I would write that in a matrix form. And this becomes the control model for the plus configuration. Everyone understood this? This is the basic quadcopter control. Now, what I want to do is, if I want to extend that to X configuration, what you do, I actually follow the same thing, but now it will become, you will have a factor square root of 2 over 2. And then instead of just changing 1, because now if you think about it, X is north, east. So if you want the whole thing to rotate, then you just can't change the speed of 2 props. You will have to change the speeds of 4 props to do it. Are you with me so far?
Yeah, is that 1 by root 2 tan theta start quadcopter?
Yeah. So basically what you do is you basically, and then that's why this factor comes in the picture. And same thing, what you do is just like what we did in the previous case, you add that in the matrix form, and that becomes the control equation for your X configuration quadcopter. And this is the very basic quadcopter control. Now the next part, and this is very interesting, is what are the forces that are actually coming on quadcopter? What are the forces? There are 2 types of forces. One is an aerodynamic force, which means as that quad is flying, the body has certain shape. So basically there is some incoming air velocity. That air is going to resist the motion of the quadcopter. So there is going to be some sort of drag. But in addition to that, if you look at the prop, as the prop is rotating, there is a trailing edge and there is a leading edge. So what happens is, initially, as the prop is going forward, it's increasing the speed. As our prop is going backward, it is decreasing the speed, depending upon whether the aircraft is moving forward or aircraft is going backward. So this differential speed causes something called as the blade flapping. And I don't know if you have seen this, it may not be visible in the quadcopters, but if you look at the helicopters flying, the big helicopters flying, where the helicopters don't take off like this. Helicopter, because the under actuated system, it basically goes like this. You will notice that the blades, that the top blade on single helicopter would be doing something like this. It will never go like this. It will be like this. Flapping occurs because of the differential speed as the leading and the trailing blade. Okay, so here is what happens. This blade flapping is an important phenomenon, and there are special techniques to compensate for that in the case of helicopters. So what you have is, as the blade is advancing through the air, and because of the motion of the air, you have upward and downward motion, and that causes the blade to flap. And this basically, this flapping effect somehow needs to be compensated, because in runtime, this flapping actually changes the effective direction of the thrust. So basically, you have to compensate for flapping. For small quads, that flapping can be ignored. But if you are looking at the big helicopters, you cannot ignore the blade flapping. The next part is, I just want to tell you that these are the basic equations. When you have a flying aerial vehicle, you are going to have some sort of aerodynamic effects. What do I mean by aerodynamic effects? As the aircraft is flying through the air is going to resist its motion. Air is going to provide some sort of drag, and that aerodynamic drag needs to be compensated or somehow taken into account by the propulsor system. And for the quadcopter flying at slow speeds, the aerodynamic drag is simply k drag times the velocity in its direction, and k drag multiplied by the velocity in y direction. So I don't know if you have seen the advertisement. Tesla has coefficient of drag 1.6, which is the lowest. Yeah, that's all. So basically that means the resistance given by the air. We want to minimize the drag as small as we want to minimize the drag so that the aircraft is efficient. And these equations we are going to discuss in a lot more detail. So more details on this will be coming pretty soon. So in this lesson, we just looked at the overview of the equations, and the next part is we want to get into the details of what those equations are. And the way I'm going to develop this is I'm going to give you some generic techniques for deriving the equations. So which means whether you have a quadcopter, whether you have a fixed wing aircraft, or whether you have a helicopter, you would follow the same principles and be able to derive those equations. So let me show you what I mean by that. And if you get a chance, I don't think I would be able to finish this in today's lesson, but at least I want to give you some nomenclature and idea. I will discuss this again in detail. So here we don't have a quadcopter. What we have is we have a fixed wing aircraft. However, coordinate frame is exactly the same. What we have is we have Earth center, Earth fixed coordinate frame. We have a north, east, and down coordinate frame. North axis is U, down axis is W, and east axis is V. And you have P, Q, and R. So those are the angular rates. So please understand, theta is the pitch angle, C is the roll angle, psi is the heading angle. In the case of quadcopters, remember the equations that we talked about, they also use the exact same nomenclature, exact same terms. The only thing is, instead of a fixed wing aircraft, what we have is we have a quadcopter. Now, next thing what I want to talk about is I want you to look at the very first equation that is shown over here. That equation is the equation for translational dynamics in Euler angle. Remember the one motion looking equation that we talked about? What that equation is, and I'm going to tell you exactly how to read this equation. You have E n dot. E n dot is the velocity in the north direction. P e dot is the velocity in east direction. P d dot is the velocity in the down direction. That velocity is equal to, I want you to look at on the right hand side, it's R V B V B. What that means? VB is the velocity of the aircraft in its body frame. So you have VB, which is the velocity of the aircraft in its body frame. You have this rotation matrix that will take you from body frame to inertial frame, and that gives you Pn dot, Pe dot, Pe dot, and Pd dot. Everyone understood this? So this equation is something like this. On one side, you have Pn north, Pe, P down. This is an inertial frame. Which is Earth center coordinate frame, Earth center, Earth fixed, is equal to. Now what you have is, you have the velocity of the aircraft. Velocity of the aircraft is VB. So which is Vx in body frame, Vy in body frame, and Vz in body field. Are you with me? This is body velocity. This is dollars to pesos. You cannot equate dollars to pesos. You need to transform either the inertial velocity into the body velocity or the body velocity into the inertial velocity. And the way we do that is we have this rotation transformation, which is inertial, or I'm going to call this E to body, which is something like 0 R1. So V1x, V1y, V1z is equal to V0x, V0y, V0z. Everyone understood this? The first equation, that motion equation, is nothing but the expanded version of this. Now you may say, oh wow, what happened now? So now what you have is, you have this transformation matrix. Remember, there were three angles. There were initial rotation about yaw, then rotation about pitch, and then there was rotation about roll. So can you see that all those angles, 0R1, 1R2, 2R3, they got combined and you got this big rotation transformation. Everyone understood this? A minute to think. It's the same transformation that I derived in last class. Remember MATLAB? Euler angles. Everyone clear about this equation? Understanding this is super important. One thing, this transformation is an orthonormal transformation, which means inverse is equal to transpose. So if someone says, hey, I don't like the velocities in inertial frame, I want to go to body, then what I would do is, rather than taking this ERB from here, I would do RBE, and then I would still write the equation. Everyone understood this? No? Okay. So this, so ERB, VB is equal to VE. Do you agree with this equation? Okay. Now, if I want to take this on the left hand side, what I will have to do is ERB inverse VE is equal to VB. Agreed? This is an orthonormal matrix. Inverse is equal to transpose. So B R E V E. Okay. All right. Now we will dissect this equation. Remember?
Hello, sir.
Yes. Question?
The background is blurred out. We can't see the equations. Well, I can't.
Okay. Background is blurred out. Okay.
Yeah, it's been like that the whole class.
If you guys have some smart way of addressing this, let me know. I really don't know what to do here, but I did camera setting. I removed the blur and all that stuff.
No, not from Zoom, from camera of your Mac.
Okay, you can show that to me after class.
I don't know.
I'm running Windows, using bootcamp. Okay. Anyway. Whew. All right. So here comes the second most important equation. Remember the kinematic equation? I told you that there are two parts. One is the position, one is the translational velocity equation, and second one is angular velocity equation. Remember linear velocity, angular velocity equation? Okay, so we finished the linear velocity equation, kinematics. Now we are at angular velocity equation. Robotics 1. How do we find out the angular velocity in inertial coordinate? Remember angular velocity in inertial coordinate. Now, online students, I don't know if you can see me. This is the equation that we derived. Three frames, 0 R0. Here there will be omega 1. And this omega 1, depending upon whether you are rotating about x-axis, y-axis or z-axis, that is where omega 1 would go. So for example, if you are rotating about first axis, it would go here. So it doesn't matter, there is omega 1 over here. Then next, 0 R0, 0 R1, and then here there is omega 2. Do you agree with me? Plus 0 R0, 0 R1, 1 R2, omega 3. Remember we did this in robotics 1. You remember this? Jacobian linear angular Jacobian of angular velocity, and then finally we combined whole thing, and then we said that you have something like omega 1, omega 2, omega 3, and then you have omega x, omega y, omega z, and this is a Jacobian of angular velocity.
Could you explain omega 1 to 3 in this context? Because in that
Omega 1, 2, 3 are the rotation rates about individual phase.
Is it in the ABCF or CCCF?
I'm not I'm on robotics 1, not in robotics 2.
In that context.
So what I mean by this is omega 1 is the angular velocity of the joint 1. Omega 2 is the angular velocity of joint 2. And omega 3 is angular velocity of joint 3. Remember?
Yeah, that part is.
Okay. Now, what I'm going to do is, this is the exact same. 0 R0 is what? Identity matrix. 0 R1 is RB V2 C. And 0 R2 is RB V2 C RB V1 theta. And please note, the rotations is phi dot. Phi dot is about x. Theta dot is about y, and psi dot is about c. So this equation, when you combine the same thing what we did in robotics 1, what you get is you get the relationship between the angular velocities in the inertial frame, Jacobian, and the angular velocities in the body frame. Everyone understood this? Let that sink in. This is an entire field, and I spent my 2 years working in that area of inertial navigation and tracking, dealing with just these equations. Put an IMU on aircraft and find out the orientation of the aircraft. You realize that you cannot solve this equation by just plugging the numbers on the right. It's a differential equation, which means you need to integrate. You agree with me? Here is the problem with integration. Every time T, Q, and R will be changing because your aircraft is rotating. So what you need to do is you need to numerically integrate, and then there is a problem. How would you find out sine phi, cosine phi, sine theta? You will find those from the previous angles of attitude. I would let this sink in, and we'll stop here. Yeah.
Left side is the IMU output.
So right hand side, PQR is IMU output.
And the Jacobian is the same as the
Jacobian changes every time because your pitch and your angle changes.
For what? The Jacobian for the region and the Jacobian for the location are the same.
No, yeah, they are different.
How different? For the same maneuver.
Linear is going straight. Rotating is
For the same maneuver. Whichever same maneuver. The Jacobian for that maneuver is the same with the case of rotation and the case of.
Jacobian for translation is defined differently as Jacobian for rotation. Jacobian for translation is just if you look at the way we derive in robotics 1, Jacobian for translation is different than the Jacobian for rotation, even though the motion is the same. The only thing is if you are getting level flight, then they may be the same, but otherwise they will be different. As soon as you have angular orientation, they will be different. Previous frame part. Just a second. Amazon, $17. Yeah, this is no, this is for members. You can get the same case for 10.
So Professor, I have a question.
Yeah.
You can stop recording.
Okay.